हाँ जी, am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Sure.
Yes, sir.
Okay, so up to last lecture, we have finished TIR, right? So we did one numerical on TIR also, no? So what are the two essential conditions for TIR, Meher? Two essential conditions for TIR. Meher. Hishma, what were the two essential conditions for a system to undergo TIR? Hishma. Conditions for TIR, essential conditions for TIR.
So that the ray should travel from denser to rare medium.
So there should be
And
two essential conditions, huh?
the
Ray should
angle of
travel from
incidence.
Denser to rarer.
denser to rarer, and angle of incidence should be greater than the critical angle. Simple two conditions. Ray should travel from denser to rarer, and angle of incidence should be greater than the critical angle. These are the two essential conditions for TIR. We did one numerical on TIR also, the numerical which use one TIR and one diffraction. That's a common type of question that one can get in TIR. There's one more question on TIR, and that question is in the assignment. Do this one. So we finished. This question. This is an important question. This is in previous years of CBSE, NEET, JEE, and all exams. So question number 4. So see, what does question number 4 essentially says? It says, question number 4 I'm discussing. Do one thing, just read this question, make a rough sketch of it, then we'll solve it. Make a rough sketch of this question.
So can you zoom it a little?
Yes, yes, yes.
Yes.
No need to write the question. You have this assignment. Just write question number and try to make a rough sketch of it. This was there in previous years of CBSE also.
Sir, question number 4.
4, yes, question number 4. Just make a rough sketch of this question. Solve it. Question 4 you have to solve. Yes, did you draw the rough sketch? Nabil, Arpit? Okay, I'm explaining the question. Question number 4. So the question number 4 simply says that you have a beaker. In this beaker, you have a light source. Let's name this light source as O. Rays are coming from this, and this is some liquid of refractive index. So this is liquid of refractive index mu, and outside you have air. So when the ray comes from denser to rarer medium, they will bend away from the norm. So let's take this ray. When this ray will comes out, it will bend away from the norm. Similarly, if you take this ray, when it comes out, it will bend away from the norm. For this particular ray, if I call this as ray number 1 and I call this as ray number 2, if I compare 1 and 2, which ray will have greater value of angle of incidence? Or angle of incidence will be same for both? Ray 1 and ray 2, which will have greater value of angle of incidence?
Ray 2.
Ray 2 will have. And similarly, if I take a ray 3, then angle of incidence will increasing. So the angle of incidence keep on increasing for the rays which are getting incident near the wall of the beaker. So this is the angle of incidence. Now, if this angle of incidence becomes equal to the critical angle, then what will happen? Will the ray will emerge out of the beaker, or it will start grazing on the surface?
It will graze on the surface.
Grazing on the surface.
If angle of incidence is greater than the critical angle, that then what will happen? Ray will reflect back into the same medium. So I can say that ray will come out of the beaker from this point A. Similarly to the right hand side. Similarly to the right hand side, you must be having a point where angle of incidence is equal to critical angle. So ray is again grazing here. Let's call this point as. So all rays which are coming in between A and B can be seen here. They can come out of the beaker. So the rays which are passing through this region A to B can come out of the beaker. The rays which are coming from the region beyond A and beyond B will undergo TIR, and these rays will not come out of it. So the question is saying the height of this region is h. You're supposed to calculate this h in terms of mu, and this radius of this particular region is r. You are supposed to relate this r, this h, and this p. This is what you have to do. So the ray which are incident on the surface beyond point B will not come out of the beaker. The reason is this ray will undergo TIR. Similarly, the ray which is incident here will not also come out of the surface. It will undergo TIR. So the ray which is incident in between A and B can come out of the surface. Now, when the question is saying that he placed an opaque object in this region, the region that I'm drawing with a red color, he placed an opaque object. Opaque object means ray will not come out of this region, cannot cross an opaque object. So there will be no ray that can come out of the surface. So he's just asking about the height h. You can relate this height h with this radius and this. So for this, what we can do is, if this angle is C, Nabil, how much this angle would be?
Yes, sir.
So I'm erasing this rays will confuse you. I'm just erasing all extra rays. So the question is very simple. The logic is very simple. The ray which are incident beyond this point A and B will undergo TIR, and the rays which are in between A and B will not undergo TIR. They can come out of it. So if this is C, this is also C, vertical alternate angles, this is C. You can relate through right angle triangle. See, if I say this is O, I call this as O1, then in triangle O1B, in triangle O1B. O1B. In this triangle, sine C is perpendicular divided by hypotenuse. So you can write that sine C is R divided by OB. Since OB is the hypotenuse of this triangle, using Pythagoras theorem, you can write OB is O1 square plus O1B square. Or you can say that OB is this side, H square plus R square. So using Pythagoras theorem, you can write this R as root over R square plus H square. That's my first equation. Hishma, are you in class? Hishma.
Yes, sir.
Hishma, can you connect this sin C to refractive index somehow? Refractive index of the medium?
Sin C is equal to 1 by India.
Yeah, sin C is 1 by refractive index of denser medium with respect to rarer. This is the formula, the only formula which is there in TIR. So this is R by root over R square plus H square. You need this H, you can just cross multiply this. We'll get root over R square plus H square is equal to NdR multiplied by R. You can take square on both the sides. When you take square on both the sides, you get R square plus H square, which is equal to N square dr into R square. You need H square. Height is what you're supposed to calculate. So you can write that your H square is N square dr into R square minus R square. Next, what you can do is you can just take R square as common. So when you take R square as common, you are left with its N dr whole square minus. So you can write that your H is its R, it's root over N dr whole square minus. Just keep on substituting the value. See how much is R. R is given in the question. Huh? So the value of R is 1 centimeter. Huh? And refractive index is 5 by 3. So this is 1. So your answer will come in centimeter. This is 5 by 3 square minus 1. So your H is 1. It's 25 by 9 minus 1. So 25 minus 9 will be 16. So that will be root over 16 by 9. So this will be 4 by 3. So this is some 1.33. So this is the height of water column up to which no ray can come out of this container. The reason is the only region from which ray can come out is this A to B region, and you place the opaque sheet over it. This is what the question says. There's an opaque disk of radius 1 centimeter floating on the surface. So the only region from where ray can emerge out is this A to B region, this region that I'm taking with the red color. But he placed an opaque sheet over there, so no light can emerge out of it. It's a very important question for you. If some tough questions comes from TIR, then it could be that question. And this is, by the way, from PYQ. Note it down, please. Question number 4 of the side.
1 है ना 1 सेंटीमीटर
1 है, yes.
सर इसमें लेकिन ये कैसे मतलब पता चला कि जो डिस्क है जब वो ए और बी पे कोइंसाइड करेंगे
कहीं भी हो सकते हैं ना ए और बी पॉइंट्स. ये पता है कि जो भी ए और बी पॉइंट्स होंगे वहां पर TIR होगा तब रे बाहर नहीं आएगी, राइट. ए और बी ये पता है ना कि रे बाहर नहीं आ रही, उसने ये कहा हुआ है. रे बाहर तब नहीं आएगी जब TIR हो रहा होगा, अदरवाइज तो ट्रांसपेरेंट है, रे को बाहर आ जाना चाहिए.
सर तो उसके एज पे ही वो समझते हैं
नहीं, वो कहीं भी हो सकता है. देखो ये बीकर है ना, यहाँ से रे कहीं भी चली जाए, एच नहीं है, कहीं भी रे डेंसर से रेयर आ रही है. मैं कह रहा हूँ ये बाहर नहीं आ रही, तो उससे आप क्या कंक्लूड करेंगे?
सर वो मैं समझ गया लेकिन ये जो डिस्क है ये मतलब इसके जो एजेस है ये ए और बी पे क्यों नहीं है मतलब कम क्यों नहीं है ज्यादा क्यों नहीं है
कहीं भी हो सकते हैं, मतलब कहीं भी हो सकते हैं, जहां भी होंगे उसे ए और बी मान लिया. आप ये कह रहे हैं 1 सेंटीमीटर ही क्यों?
नहीं सर मतलब ए एंड बी तो वो पॉइंट है ना जहाँ पे मतलब क्रिटिकल एंगल बनेगा
हाँ हाँ, अब ये कहीं भी हो सकता है सिस्टम में. एंड देखो ये जो रीजन है हमने जो कैलकुलेट किया, दिस डिपेंड्स अपॉन कि रिफ्रैक्टिव इंडेक्स क्या है और हाइट क्या है. सो मैंने कोई फिक्स वैल्यू नहीं ली. योर आर डिपेंड्स अपॉन रिफ्रैक्टिव इंडेक्स इन एच. ये कहाँ जाएगा, दैट विल डिपेंड कि रिफ्रैक्टिव इंडेक्स कितना है। अगर आप रिफ्रैक्टिव इंडेक्स चेंज कर दें तो शिफ्ट हो जाएगा। मतलब सिर्फ ले कहीं तो होगा ना, जहां होगा वहां तक का सेपरेशन आया, और कहाँ तक होगा दैट डिपेंड्स अपॉन द रिफ्रैक्टिव इंडेक्स एंड हाइट। I hope it's clear now.
Yes.
Miraj, where were you in the last classes? Miraj Rahman.
Sir, I'm having my practical pre-board practicals currently.
मिराज कभी फाइनल एग्जाम्स होंगे बोर्ड्स के? ये इस साल नहीं है?
Sir, हैं?
हैं? उसमें भी तो कुछ पढ़ना पड़ेगा, कैसे करोगे इतनी क्लासेस अगर मिस करोगे?
नहीं, सर, वो
स्ट्रेटेजी
लेक्चर
है?
देख लिया था।
यार मिराज देखो, लाइव क्लास की बात ही अलग होती है ना,
Yes, sir.
रिकॉर्डिंग से तो नहीं होता सब कुछ। Can I scroll it now? Saifullah, where were you in the last 1 week?
Sir, I had exams.
How will you cover it? कुछ मिस किया?
Sorry, sir, can you repeat?
How would you cover it, whatever you have missed in the last 2 weeks? Like you have missed a good portion of wave optics and ray optics both.
Sir, I will try to complete it by this weekend, Friday and Saturday.
Okay, I hope you all have written it together. So after this numerical, there are some applications of TIR. Applications of TIR. So the first application is sparkling of diamond. See, for a diamond, the critical angle is 24.4 degrees. So once a light ray enters into the diamond, it gets trapped into it. So if you take example of this particular light ray, so if you take this example, this is a light ray. This light ray enters into the diamond. When it enters into the diamond, it gets refracted. Now it gets incident over this particular phase. And let's say this is the normal. In diamond, the angle of the critical angle is very small. It's 24.4 degree. So the ray which tries to come from this face is very likely to have angle of incidence greater than this 24.4 degree. Means angle of incidence will be greater than critical angle. If angle of incidence is critical angle, then ray will reflect back into the same medium. Same thing can happen here. Again, rays trying to come from the denser to the rarer medium, but angle of incidence is again greater than critical angle. So ray will again reflect back into the same medium. Again here. So the light ray gets trapped within the surface of diamond. So that's why the diamond sparkles. It's due to the trapped light ray. And the reason is the smaller value of critical angle, 24.4 degree. As compared to diamond, if you take any other prism, then critical angle is around 42 degree. So it's very unlikely that light get trapped into another prism. But if you
Sir,
take
but
diamond,
why?
it's because the refractive index of diamond is very, very high. It's very high as compared to a normal glass. If we take sin C, then sin C is 1 by refractive index. For diamond, refractive index is very high. That's why critical angle is very small. So lights get trapped into it. If you take a normal glass, then refractive index is small. So critical angle is around 42 degrees. So these are some theoretical applications. So what you can do is you can just take screenshots. We don't invest time in writing it. Just take screenshot of this thing. Take screenshot of sparkling of diamond. The second application is mirage. See, mirage and looming are two types of optical illusions. So to explain mirage, I choose this video. So yeah, can you see this video, this animation?
Yes, sir.
Okay, this is mirage. See the reflection that you are getting here. This reflection seems like there's some water on the surface, but this is a desert. There is no water here. The reflection of the atmosphere or the reflection of sky can be seen on the sand surface. So this is what you call mirage. It seems like some water, but there is no water. It's an optical illusion. It's simply sand. But you can see the reflection of the sky over the sand. So your brain will interpret it in a way, okay, that there's some water here. This optical illusion is known as mirage. There are some more examples of mirage also. Where is it? Yeah, this is very common. So when you're driving somewhere, if a very, very hot climate around, if the temperature is around 40, 42, then it seems like on the road some water is there. Basically, there is no water. You are looking the reflection of the atmosphere on the road, and your brain will interpret, okay, there is some water here. So this optical illusion is again mirage. There is no water here. See, you can see the reflection of this tree over the road. There is no water. It's simply an optical illusion. You can see the reflection. You are actually seeing the reflection of the atmosphere on the road. So this optical illusion is mirage. So what exactly happens in mirage is yeah. So what happens in mirage is the light rays which are coming from this object, these rays, they get totally internally reflected. The reason is as you go up, see this is sand. Here temperature is let's say 45 degrees Celsius. So its refractive index is very small. As you go up, the temperature keeps on decreasing. So temperature decreases, that means refractive index increases. If you go up, that means your N increases. So the light rays which are coming from this tree is coming from a region which is denser to a region which is comparative rare. So the first condition of TIR gets satisfied. After multiple refraction, what happens here is the angle of incidence becomes greater than the critical angle. I is greater than C. So due to which the light ray bends, they bends and they enter the eyes of the observer, and this eyes will interpret it in this way that the image is here. If this is the observer, and let's make it lengthy, this is the observer, the light rays will enter in the eyes of observer.
So can you explain again?
Huh. In the first lecture of refraction, we have discussed that refractive index is inversely proportional to the temperature. So if you take this particular example of sand, then temperature at the sand is highest, and as you go above in the atmosphere, the temperature keeps on decreasing. So if here temperature is 45 degrees Celsius, you can say here temperature will be 40, here temperature will be 35 and all. Temperature is decreasing. If temperature is decreasing, that means refractive index is increasing. N increases. Means here the region is denser and here the region is rarer. Is it clear, Arpit?
Yes, sir.
So rays are coming from denser to rarer medium. That means first condition of TIR is getting satisfied. Now the rays coming from here will suffer multiple refractions. And after few refractions, what happens here is the angle of incidence becomes greater than critical angle. What happens if angle of incidence is greater than critical angle? TIR happens. So the ray will reflect back into the same medium.
So the multiple refractions take place due to the change in temperature, right?
Change in temperature. Different layers have different refractive index. This is the reflected light. When this ray enters in the eyes of the observer, the eyes will not I will always see in the straight line direction. So I will interpret that the rays are coming somewhere from here. I will not interpret it to be here. Your eye will interpret it to be somewhat here. So you can literally see the image of this tree on the ground. I believe they must have done this. We'll see the reflection of this tree on the ground. And that optical illusion is actually TIR. Yes. So see, you can see the reflection of this tree on the ground. So when your eyes see the reflection of tree on the ground, then it interpret, okay, there should be some water here, which is reflecting the rays coming from here. But it's not water which is reflecting, it's TIR which is reflecting. So this optical illusion is known as mirage. Simple application of TIR. Is it clear? What is mirage exactly and how does it happen? Anshika, Nabil, Omar?
Yes. Yes, sir.
Okay. There is one more application of TIR which happens in a very, very cold climate. And that is known as looming. Yeah, this is true. So loomings occurs in very, very harsh climate. Like if the temperature is very low, then you will observe looming. And in looming, what happens is the ship which is on the ground, it appears to be floating. This is looming. This is the actual photograph of the ship. So ship which you assume is floating on the water, it appears to be floating on in the air. This is looming. So it's just reverse. In extreme cold conditions, what happens is here temperature is low. Temperature low means here temperature is very low. Let's say here temperature is minus 10 degrees Celsius. Here temperature is minus 8. As you go up, temperature increases. It's 0 degrees Celsius. So here where temperature is low is the denser medium, and here is the rarer medium. Say there is one ship here. So the rays coming from the ship are actually moving from a denser to a rarer medium. They gets refracted here, TIR. And if there is some observer here, he will see that the rays are coming from it. So the ship which is floating on the water, it appears to be floating in here. This optical illusion is known as looming. So looming and mirage occurs in extreme conditions. Mirage in extremely high temperature, looming in extremely low temperature.
So this optical illusion can also be captured by a camera lens.
Yes, it can be captured. I believe yes, it can be captured. So this is Mirage. You can take screenshot of this thing. It's a theoretical thing. It's nothing which I can show it. Just take screenshot of.
Sir, could you just zoom up 1 second?
Mhm. Can I scroll?
Yes, sir.
See, Omar, what's happening here is this is the ship. Here, it's a very high, low temperature and it's comparative high temperature. So at ground, you have denser medium and here the medium is rarer. So the ray coming from the ground is moving from denser to rarer medium. Then it gets reflected due to TIR. And if this is some observer sitting here, the ray will appear to him to be coming from this direction. So the ship which is floating in the water will appear to be floating on in the air. Our eyes always see in the straight line. So your eyes will see this object to be here. The ship which is floating on the water will appear to be floating in. That's looping. Okay, after this, the next important application is totally reflecting prism. Say, prism is a transparent thing. So prism should refract light rays. But using prism, you can also reflect light rays. So it's a 45-degree, 90, 45-degree means in prism, one angle is 90-degree, two is 45 degree. That's a totally reflecting prism. If you take the critical angle for a prism, then the critical angle for the medium of prism is 42-degree. See, this is very, very high as compared to the critical angle for diamond. For diamond, it was 22.5 degree. So your prism can deviate your light ray by 90-degree and it can also deviate your light ray by 180-degree. See how it will deviate your light ray by 90-degree. This is your prism. This angle is 90-degree. This angle here is 45-degree. And this angle here is also 45-degree. So you incident a light ray in this direction. This is how you incident the light. This is the normal. So this ray enters normally into the prism, so it will not refract. There is no refraction here. But when this light ray is incident over this point, this is 90, this is 45. How much is this angle, Noha? This angle? How much is this angle? This is 45, this is 90, this third angle. Noha.
So 45.
This is 45 degree, huh? If this is 45 and this hole is 90, then how much is this angle? This is again 45 degree. That's your angle of incidence. And if you can see here, the critical angle for the material of prism is 42 degree. Anshika, will there be TIR here over this point? Is there any possibility of TIR here? Anshika. See here, the ray is traveling from glass to air. So the first condition which says ray should travel from denser to rarer. The first condition is getting satisfied. Second, your angle of incidence is greater than critical angle. Critical angle is 42 degree. Angle of incidence 45 degrees. Second condition is also getting satisfied. So your ray will reflect. It will undergo TIR. Again, it's normal over this face. It will go straight. So you can see your ray bent by 90 degree. Using prism, your ray bent by 90 degree. It deviates by 90. You can also do image formation from here. Like if you take an object, you put this point as A. So this will be some A prime. And you take this point as B. So ray goes here and then it comes here. This point is B prime. So this B prime to A prime. This is how it bends. This is B prime to A prime. So the object which was erect will get deviated by 90 degrees. So you can also study image formation using a prism. This is how you build a periscope. Is it clear how this prism can deviate a ray by 90 degree?
Yes, sir.
Sir, can you explain again?
Yes, Sapula. See, for TIR, the condition is angle of incidence should be greater than the critical angle. For the medium of prism, the critical angle is 42 degree. So just by using this geometry, this ray is incident normally on this face of the prism. So if a ray is incident normally, it will not deviate, it will go straight. Then this ray is incident here. This is 90 degree, this is 45 degree, and this is 45 degree. This is the normal. If this is 45, this hole is 90, then this angle will be 45 again, right? 45, 45 will make 90. This is your angle of incidence. If your angle of incidence is greater than critical angle, which is for a prism, it's 42 degree. Then ray will reflect back into the same medium. It will undergo TIR. So it will reflect back here, undergo TIR. So the two essential conditions for TIR, first, your ray should travel from denser to rarer. So ray is traveling from glass to air. The first condition is getting satisfied. The second condition is angle of incidence should be critical angle. And this is how the second condition is getting satisfied. Angle of incidence is greater than critical angle. So it will reflect back into the same. Clear, Saifullah?
Yes, sir.
Next, using the same prism, you can also deviate your ray by 180 degrees. See, 180 means you take this prism. This angle is 90 degree. This is 45 degree. And this is again 45 degree. So rays are coming like this. Over this face, your ray is normal. Normal incidence. So there won't be any refraction. It will go straight. Then this is the normal. This angle is the angle of incidence. You want to calculate this angle of incidence. This is 90, this is 45. This angle will be 45 degree. So this angle here is again 45 degree. This is 45 degree angle. So your ray will undergo TIR, one TIR here. Then again over this face, you can prove that angle of incidence is again 45 degree. If this is the normal, and this is your angle of incidence, this is again 45 degree. It will go one more in TIR and ray will reflect back into the same medium. So ray will deviate by 180. Getting deviated by exactly 180. So if you just change the orientation of the prism, then it can deviate your right ray by 180 degree also. Just take the screenshot of this. We'll start spherical refracting surface. And you have test after the class, right? Current electricity.
Yes, sir.
Okay, from next week onwards, I'll take test on Friday. Like your exams are coming, so I believe you're not going out on Friday. Huh? So Friday, let's keep every Friday for fixed for test.
Sir, from next Friday, I'm having my pre-boards.
Ah, very good. Then you should give test also. Huh? You must have prepared all topics for your pre-boards. So the next test would be for chapter number 4. Not this Friday. I took test on Wednesday, so I'm not taking any test on this Friday, but for the next Friday.
So what will be the timings?
Give 2 options. One will be in the morning, 9 to 12. And so test will be all 3 subjects, physics, chemistry, and maths. So all other teachers will announce their revision test series. So we'll have 2 options, either 9 to 12. 9 to 12 means it's 11:30 to 2:30 IST, or in the evening. You can give test in the evening also. 7 to 10, I believe, would be the time. So we'll take for 50-55 minutes test of each subject. And these test papers will be strictly based on your board's patterns, basically. Did you solve the assignments that I gave you yesterday? Last class? No. Does anyone solve the assignment?
Sir, could you zoom up a bit?
So the ray optics worksheet.
Yeah, the optic version.
Yes, sir.
See, if you start solving these assignments, then I will share some revision assignments also. Otherwise, it will be wastage of my time and energy if you're not solving it. If you're solving the assignment, then we can share the assignments of electrostat and all chapters. Strictly based on the CBSE pattern, and there will be level-wise questions. You can have questions for JEE also. I believe you have taken screenshot. Just take screenshot.
सर अभी वाले टेस्ट में डेरिवेशंस भी आ सकते हैं.
But usually मैं derivations नहीं देता. I assume कि आप इतने mature हैं कि derivations तो करके जाएंगे. But you should prepare derivations. You get in boards exams, you will get derivations also. No? So don't skip derivations, but test में derivations कम होगी. Major it will be numericals and conceptual questions.
Okay.
And also try to give you a list of all important derivations chapter wise. I believe you have taken screenshot here. Okay, there is one more application of TIR, which is basically optical fiber. Optical fibers are wires which are used for communication. Like all internet wires are optical fibers in nature. So this I leave for you. Write a short note from NCERT in optical fiber. There's no calculation here, just theoretical thing. You should remember that optical fiber also works on the principle of TIR. Just note it down. Write a short note on optical fiber from NCERT. So that was about plane surface. The next is refraction through the spherical surfaces. Spherical surfaces are more important than your plane surfaces. If you take the pattern of boards or any entrance, the major questions comes from spherical refracting surface. So how to make a spherical refracting surface? So you take a glass sphere. You take a sphere, glass sphere. The center of the glass sphere is C. The radius of the glass sphere is R. The medium inside the glass sphere is N2, and the medium outside the glass sphere is N1. So if you cut a portion of this glass sphere, you cut this much of portion, then this portion here will behave like a spherical refracting surface. Lenses are combination of 2 or more spherical refracting surfaces. So if you have 2 or 3 spherical refracting surfaces, then they will combine to form a lens. So this is the foundation of lens, basically spherical refracting surface. You cut this much of portion, this much of portion here, then this portion will be a spherical refracting surface. Now, this surface is convex or concave will depend upon the rarer medium. If your surface is convex towards the rarer medium, then it's a convex refracting surface. Say this is my rarer medium, and the surface towards the rarer medium is convex. This bulged surface is known as convex surface, and this is known as the concave surface. So the surface towards the rarer medium is convex. We call it a convex refracting surface. If you take this example, it seems identical. But if you look at the rarer medium, this is rarer medium, and face towards the rarer medium is concave. So we call it as a concave refracting. So it is concave towards the rarer. So we will deal with these two types of surfaces, a convex surface and a concave surface. For spherical refracting surfaces, we use few terms. We use a term which is known as center of curvature. So what does center of curvature means? Center of curvature is the center of the sphere of which the surface is a part. So you cut this surface from a sphere. The center of the sphere is the center of curvature. The radius of the curvature, the radius of the sphere from which you cut this spherical refracting surface is radius of curvature. Center of this spherical refracting surface is known as pole. This is the pole. And the separation between center of curvature and pole is known as radius of curvature. Next, we will be using a sign convention. So the sign convention says, measure all distances from pole. All distances from pole means, let's say I place an object here. I ask you to calculate the distance of this object. So measure distances from pole. Starting point for measuring all distances would be pole. You'll start from pole and then you will go to the object. You will not go from object to pole. This is wrong. You will start from pole and will go to object. So if similarly here, if you have something, some images here and asking you to calculate this distance, you will start with pole and go here. If you are going in the direction of light, say this is the direction of light. If you are moving in the direction of light, say from pole to here, the arrow is in the direction of light, then that distance is positive. But if you are going in a direction which is opposite to the direction of light, then your distance will be negative. This is the sign convention that we'll be using. So the first point of sign convention is all distances are measured from pole. I'm repeating again, starting point for measuring all distance is always pole. You start from pole and then you'll go to another body. You start from pole and then you will go to another body. Second, distance and direction of incident light are positive and direction opposite to that of light are negative. Let's take one more example. Let's take this example here. And this is the rarer medium. This medium is rarer. This is the rarer medium. Anshika, is this a convex surface or a concave surface? Anshika, this
So
surface
concave,
here. Concave.
convex,
Convex. Mehraj, is this a convex surface or a concave surface?
Convex.
Convex, because towards the rarer medium, you have a convex thing. So it's a convex refracting surface. Okay, note it down. Then we'll see how many derivations we can do on this thing. Note it down. The spherical refracting surface along with lens maker formula are usually a 5-marker question.
Sir, only the left figure or the right ones also, sir?
Both. The left one is for convex surface, the right one is for concave. So this is the rarer medium which will decide the shape of the surface. But there's a thing, it does not matter what is the shape of the surface. Your calculations will not change by the shape of the surface. But you should at least know by looking at the surface whether it is a convex or a concave surface. But even if your judgment is wrong, you instead of convex, you write it as concave. But if you are using the right formula, then your calculations will not change. The formula will not depend whether your surface is convex or concave. You'll get the same formula for both convex and concave surface. Just tell me once you have written up.
Done, sir.
1 minute, sir.
Can I scroll it now? Omar? Omar, Arpit, Munib.
Yes, sir.
अरे भाई लिखा
No, sir.
सो जाते हो तुम
Yes, sir. Done.
हाँ जी written
Yes.
Yes, sir.
okay note down sign conventions now Miraj, how will you decide whether a surface is concave or convex? Spherical surface is convex or it's concave?
Sir, sir, we can decide it by the sign convention, ma'am. Sir, if it is positive, if it is negative, then it is concave, and if it is positive,
Nah,
then it is
nah,
convex.
nah. Omar, can you explain how can we decide whether the surface is convex or concave?
So by the rarer medium.
By the rarer medium, Miraj. If it is convex towards the rarer medium, then it's a convex surface. If it is concave towards the rarer medium, it's a concave. Okay? You're not listening, Miraj. See, it's written over here also. Convex towards the rarer medium, so convex. Concave towards the rarer medium to concave. Haji Miraj, clear?
Yes, sir.
Sir, can you read out the second point?
Distances in direction of incident light are positive and in direction opposite to light are negative. So all distances which are in the direction of incident light are positive and the direction opposite to light are negative. Okay, so you must have written up to here. After sign convention, let's see the number of cases that you can make using spherical refracting surface. The first thing is, in spherical refracting surface, you can take refraction from rarer to denser medium. Refraction from rarer to denser medium means your object is in rarer medium and your image will be in denser medium. Refraction from denser to rarer means your object is in denser medium and your image will be in rarer medium. Or you can say rarer to denser means your object is in rarer and your observer is in denser medium. Your object is placed in a rarer medium and the one who is observing that object is placed in denser medium. If I say refraction is from denser to rarer, that means your object is in denser medium and your image or your observer is in rarer medium. So this is the position where you have your object and this is where you have your observer. This is where you have your object. And this is where you have your observer. Next, this diffraction from rarer to denser can be divided into two categories. It could be from a convex surface or it could be from a concave surface. Similarly here also, it could be from a convex surface or it could be from a concave surface. Now, this refraction from convex surface can be further divided into two parts. You have a convex surface, you can have a real image, or you can have a virtual image. Similarly, for a concave surface, you can have a real image or you can have a virtual image. Similarly here, you can have a real, virtual, real, virtual. So if you count totally, you have 8 cases. But for all these 4 cases, you will have same relation. Means if refraction is from rare to denser, you will get same relation whether you have a convex surface or you have a concave surface. You will have same relation whether you have a real image or you have a virtual image. Similarly here, if your refraction is from denser to rarer, you will get same relation for convex and concave surface. You will get same relation whether your surface is real or your image is real or your image is virtual. So we have two set of formulas. One is for rarer to denser, another is for denser to rarer. But if we want, we can combine these two formulas into one also. You can write one single formula which is valid for all these 8 cases. You have total 8 cases. But we won't make things very complicated. We will derive two formulas, one for rarer to denser and another for denser to rarer. But I'm saying again, if you want, we can derive one single formula which is valid for all 8 cases. That's possible. In CRT, give this derivation in this way. He gives a single formula for all cases. But when you do numericals or when you do other derivations based on this particular derivation, you can get confused. So I will not write one single formula. I will write two formula. One for rarer to denser, another for denser to rarer. Note it down. Write down all the cases. See, this is the foundation of lens. This is the foundation of lens. If you know this spherical refracting surface, you know lenses. Lenses are nothing but the combination of two spherical surfaces. Umar, clear? All cases?
Yes, sir.
You all should switch on your videos. Like, it helps you to focus. Even in your offline school classes, people can see you. Same thing is here. You should switch on your videos. एटलीस्ट मेरे लिए आसान हो जाएगा. मेरे लिए कभी कभी बहुत कंफ्यूजिंग होता है डिसाइड करना कि समझ आया या नहीं आया. फेस एक्सप्रेशंस बहुत कुछ बता देते हैं. पर एटलीस्ट पता होगा ना तुम्हें वीडियो ऑन होने वाली है, तो तुम भी जरा तरीके से बैठोगे, लेट के नहीं पढ़ोगे. और रियली ऑनलाइन क्लासेस में अगर आप फोकस करना चाहे बहुत आसान होता है. बहुत हैवी सा हेडफोन लो, इट विल जस्ट कैंसिल द आउटसाइड नॉइज. लाइट ऑफ करो, लैपटॉप के लाइट सिर्फ चलने दो. मे बी आइस पे थोड़ा सा असर पड़ेगा, बट एक दिन में 3 घंटा और 1.5 घंटा अगर आप पढ़ रहे हैं.
So what is that number at the end? 5 centimeter?
This no number. This line.
Yeah.
Same. You have same formula for all
Yeah.
4 cases. Same
Okay.
formula for all. Yes, Arpit. I would recommend if you all can switch on your videos. See, I always use focus mode, so don't worry about the recordings and everything. Anshika, written? Anshika, okay.
Sir, I'm doing it.
Okay, good. Okay, written, I believe. Huh? Anshika, written all cases?
Yes, sir.
Okay, let's start with the first calculation. So this is for refraction from rare to denser for a convex refracting surface. So see what we are supposed to derive here. We will try to relate the radius of curvature of the surface, the refractive indices, and the object distance and image distance. We'll connect all those things. We'll try to connect this distance. This one, the radius of curvature. This is your object, so this is your object distance. This is your image, so this is the image distance. The refractive index and this refractive index. We'll try to connect them. This is the formula for spherical refracting surface that you have to detect. See, the best thing about the derivations of refraction is they are repeated. You'll repeat one thing by. So let's understand this ray diagram first. I'm drawing this ray diagram. So see, it's a very, very simple ray diagram. You have this thing. You have a convex refracting surface. This is the convex surface. This is N1, which is rarer, and this is N2, which is denser. This is your object. You incident your ray here. And this is the center of curvature. So how will you drop normal over this point? Because ray will deviate, or it will refract depending upon the normal always. It will bend towards the normal or away from the normal. How will you drop normal over this point? It's an open question to all. Yes, this is the point of the surface. How will you drop a normal over this point?
Sir, connect the center of curvature with the
Hmm.
point.
Yes, you will connect this point with the center of curvature. This is how we drop normal over this point. We connect this point with the center of curvature. See, ray is coming from rarer to denser. If there is no refraction, then it will go straight. But due to refraction, it will bend towards the normal. This will bend towards the normal. So this will be your final image. And this is your object. This angle here is your angle of incidence, I. This is the refracted ray. This is the normal angle between them. Here is the angle of refraction. Then you put some arbitrary name. So this is your object. I call this angle as alpha. I will call this angle as beta, and I will call this angle as gamma. Then also put a normal here, and I call this point as n, and this is the pole. So what is the name of this distance, Ishma? Ishma, O to P. What is this distance? What is O?
Object.
Object distance. So we represent object distance with U.
U.
This is image. So what is this distance? Image
V.
distance. V. And which one is this distance? Radius of curvature, R. So this is how you can relate UV and R. The next task is to apply Snell's law. Do one thing, just draw the ray diagram. You can use anyone. Draw the ray diagram. We'll start calculations when you draw the ray diagram. So remember, if you have a spherical refracting surface and you want to draw a normal, so just join that particular point with the center of curvature. That line would be the normal on the sphere. If you have a plane surface, then it's easier to draw normal. Just put a perpendicular. But if you have a curved surface, then the normal is the radius. So join that point with the center of curvature. So that radius would be the normal of the. और वो जितने स्टूडेंट्स हैं ना जो मोबाइल फोन हाथ में लेके ड्यूरिंग क्लास घूमते रहते हैं पूरे घर के अंदर, आप कुछ नहीं सीख रहे हो, जस्ट वेस्टिंग योर टाइम.
सर कन्वेक्स रियल इमेज बनाता है?
हाँ, दोनों बनाता है, रियल वर्चुअल दोनों. It's a surface, not a mirror. There's a convex mirror which makes virtual image.
सर तो ये बेसिकली लेंस है.
Lens. जैसे जितने होंगे ना जो मोबाइल फोन हाथ में लेकर टहल रहे होंगे या बेड पर बैठे हुए कर रहे होंगे, जस्ट वेस्टिंग देयर टाइम. दिमाग ऐसे नहीं सीखता. There's a difference in attending live classes and watching movie on Amazon Prime. Yes, done. Up to ray diagram.
Yes.
Okay, let's use Snell's law now. So we'll always apply Snell's law in product form. So the product form is here the refractive index is N1, angle of incidence is I. Here refractive index is N2, angle of refraction is R. So we'll write this as N1 into sin I is equal to N2 into sin R. So first thing. The next is throughout lenses and spherical refracting surfaces, we use small angle approximation. We assume that the size of this surface, size means here to here, the size is very small. Aperture is very small. If aperture is very small, then this surface will behave like this is a very small surface, small aperture. So if aperture is small, then this I and R and alpha, beta and gamma or angles are small. If angles are small, you can use small angle approximation. Small angle approximation simply says that sin I will be equal to I and sin R will be to R. Sin R. So use this thing. I. Instead of sin I, we write I. Instead of sin R, we write R. That's small angle approximation. So that's the first part. The second part is you have to convert this I and R in terms of alpha, gamma, and beta. So for this, we use some triangles. Like I use this triangle O. Let's call this point as M. This is M. OMI. In OMI, which one is the exterior angle, Nabil? In triangle OMI, which angle is the exterior angle?
M. Sorry.
This
I,
one.
I.
I is the exterior
I.
angle. Yes, you can write that I is alpha plus beta. So I is alpha plus, sorry. No, not OMI. It's OMC, this triangle. This is the ray, this ray is coming straight, not this one. This is the straight. So in OMC, this I is the exterior angle. So alpha plus gamma will be equal to 1. See, for this triangle, this ray will go in this. So I will not be an exterior angle for OMI.
Sir, what you said, alpha plus gamma is equals to I.
Yeah, alpha plus gamma will be equal to I. You can say that alpha plus gamma equal to I. Similarly, if you take this triangle MIC, in MIC, R plus beta are the interior angle and this gamma is the exterior angle. So you can write that gamma is R plus B. So you can write R is gamma minus. So in the first step, you have to apply Snell's law. In the second step, using the condition for the exterior angle of triangle, you have to convert this I and R in terms of alpha, gamma, and beta. In the next step, what we can do is we can just substitute the value of I and the value of R from here in this equation. So it will be N1 alpha plus gamma and N2 gamma minus beta. Yes, everyone. Is it clear up to equation number 4? Anshika,
Okay, I
Umar,
have equation 3 only.
So can you
or
explain
equation,
again?
which equation over?
Please, sir.
3. It's okay. So see, in equation 3, this is the triangle that I'm taking. I'm taking this triangle MIC. This one MIC triangle. In this MIC triangle, this one is the exterior angle, right? So this exterior angle should be the sum of interior opposite angle R plus beta. So can I write gamma is R plus beta? So this is what I'm writing. Gamma is R plus beta. So you can write R as gamma minus beta. Clear now?
Yes, sir.
So for this, I'm using a triangle, which is the triangle here. It's OMC I'm using. OMC. And for this, I'm using triangle MIC. MIC. So R is gamma. Over. Clear up to 3?
So can you explain the third one again?
Third one again. See, this is the triangle. Read the name of the triangle, MIC. Which is the
Yes, sir.
exterior angle in MIC?
So gamma.
Gamma. So you can write gamma as R plus beta, interior opposite angles.
Yes, sir.
So what will be R, gamma minus beta? Let's take it here.
Okay.
Now substitute 2 and 3 in 1. When you do the substitution, it's N1 gamma plus alpha, N2 gamma minus beta. So instead of I wrote alpha plus gamma. Instead of R, I write gamma minus beta. See, this is the checkpoint. In this equation, you can check whether your calculations are going in the right direction or not. If you have gamma on both the sides, that means you're going in the right direction. Say if here instead of gamma you have alpha plus beta, that means your calculations are going in the wrong direction. You can check your calculations for the first checkpoint. You can write in some language that on both the side you should have gamma. If you don't have gamma, that means your calculations are going in the wrong direction. It's a very lengthy calculation. If you make mistake here, then you will not get the final result. Do one thing, just write down up to equation number 4, then move forward. You have test also na, from 10. And yeah, please don't cheat from Google or anywhere else during test. It's very easy for you to cheat in online exams. If you are not performing well in your exam, we will do something else. I will call you for some self-study session. We'll give extra classes. But you just cheated from somewhere and you score well, then it won't be beneficial for you. Just write up to equation number 4. The rest I will explain. Yes, written up to equation number 4.
Yes, sir.
Okay. Now let's see the next part. The next part, you need the value of this alpha in terms of the site. So look at this triangle OMN, this triangle ONM. Hishma, what is tan alpha in this triangle in ONM? Ishma, tan alpha, OMN triangle.
So MN by ON.
Yes, MN by ON. That's tan alpha. And if I take small angle approximation, then I can simply write tan alpha is almost equal to alpha, which is perpendicular MN divided by ON. Instead of ON, I'm writing NO. Similarly, which triangle you will use for tan beta, Anshika? Just look at this ray diagram. For tan beta, which triangle you will use? Anshika. Saifullah. Which triangle you will use for beta?
MNI, sir.
MNI. So in triangle MNI. Triangle MNI. Your tan beta is, it's MNI. Tan beta is perpendicular upon base, MN by NI. Similarly, for tan gamma, Maharaj, which triangle you will use? Maharaj, hai, Maharaj, which triangle will you use for gamma? जैसा लगता है महराज के साथ लैग बहुत है, पहुंच ही नहीं आवाज. महराज.
So triangle MNC.
Triangle MNC. This is triangle MNC. So how much is tan gamma? Mn by Nc. So this is Mn by Nc. Next, what you can do is you can substitute all these values here. Instead of gamma, you can write Mn by Nc. Alpha, you can write Mn by No. Similarly, gamma and this. So see, this Mn will get cancelled out from all sides. Now, note down up to equation number 8. Then I just multiply this N1 with this Nc. So N1 by Nc, N1 by No, N2 by Nc minus N2 by No. Do it. Note down up to equation number 8. Just 2 more steps and this derivation is over. And it could be a 5-marker question in your exam. If you look at previous year's questions, in a week, we'll share previous year CBSE questions with you. We're just making the question bank. So in a week, we'll share questions of all subjects, at least last 6-year questions, subject wise, chapter wise. So if you look at previous 5 years question, you will find this derivation in almost 3 years. Very, very important derivation. Tell me when you have written up to equation number 8. Just one more thing. मैं अभी कुछ दिन के लिए मैंने JEE की classes रोकी हैं, just because you people were missing classes for a school exam. So I believe I should first finish the test series, keeping your boards in mind, and then we will start it again, keeping your JEE in mind. Because you're missing too much of classes for school exams. I can't train in this way for JEE. So once this test series is over for the first book, maybe by the time we finish refraction, we can complete the test series for the first book. Then we can start with JEE. And also the JEE is in April, first attempt is in April. So we'll have 1 month after exam also. So after exam, we will focus only on JEE. And see all questions
sir?
that, yes,
So can you explain again after equation 4?
equation 4, yes.
Sir, why we are subtracting N2?
Subtracting which one? No, we are not subtracting, I'm just substituting it here. Here it's gamma minus beta. So instead of beta, I'm writing this term. Okay. I
Yes,
just
sir.
put these values here. Yeah. So you look at this triangle, Umar. OMN. Is it visible?
So which one?
OMN. OMN.
Yes, sir. Visible.
What is tan alpha in this triangle?
Then alpha. There ON.
Oh, tan is perpendicular by base. MN by NO, right?
Oh yeah. I mean by
So I wrote the same thing. MN by NO. Fine. Similarly, look at this triangle IMN. What is tan beta in this triangle?
Sir, Mn by Ni.
I see. Fine. The same
Yes.
way. Look at triangle MNC. What is tan gamma?
Sir, Mn by Nc.
So you all have written up to this equation number 8?
Yes, sir.
Yes, sir.
Okay,
Yes,
we'll
sir.
stop here. We'll stop here. We'll complete the derivation in the next class. I'm starting
Sir,
the
I
test.
haven't written wait, sir. Let me take
Okay,
the
just,
screenshot.
okay, just note it down. I'm starting the test. So it's a 50 minutes test. So you have to switch on your videos during the test. Huh? And please don't copy from Google or anywhere else. I'm not going to share this test result with anyone else but you. और ऐसे भी यार छोटे छोटे चीजों के लिए क्या ईमान खराब करना Give me 2 minutes. I'm sharing the question paper.